Okay. Today we'll go ahead and we'll finish up the free radical halogenation. So where were we at on Wednesday? On Wednesday we talked about taking an alkane, doing free radical halogenation on it, which means that we'll substitute a hydrogen for a bromine or a chlorine in the reaction. So we were at the point of saying, okay, for propane, there's two different products that you can get, product A and B. Product A coming from replacement of any of the CH3 groups, product B coming from any replacement of any of the CH2 groups. And so the major product of the reaction, what is that? It's going to depend. And it's going to depend on a couple of things. It's going to depend on whether we use bromine or chlorine, because they'll give slightly different results. And then it's also going to depend on, bromine versus chlorine. And then also it's going to depend on whether we do the reaction with light at room temperature or we do it at greater than 300 degrees Celsius. So high temperature or relatively low temperature conditions. And just so you know, you might see H nu as light. That's an abbreviation for a photon of light. So you'll either see light or H nu. So that's what the reaction is going to depend on. That's what the major product is going to depend on. We can actually quantify this. So last time we basically brought it down to two competing things. What I call statistics, and then, for lack of a better word, I'll call stability. Statistics meaning that there are 6 A hydrogens versus 2 B hydrogens in this reaction. Okay. And notice that I'm counting the original number of hydrogens over here in the reactant. So there's 6 hydrogens that will give us product A. There are 2 hydrogens that will give us product B. So that means statistically A should be favored 3-to-1. Then stability-wise, a primary radical gives us product A, but a secondary radical gives us product B. And because the secondary radical is more stable, just like a secondary carbocation is more stable, we could have a situation where the major product comes from the most stable intermediate. So these two things are fighting against each other. And so which one wins? It depends. It depends on what conditions we use. So that's where we were at the end of class on Wednesday. So that we're all in the same place, including me. So where do we go from here? Well, let's say that I want to take out the statistics. So what I do is I go to the lab, I do this reaction. Again, I'm only going to look at the mono substituted products, which is virtually impossible, but that's what I'm going to look at. So I go to the lab, I react my bromine with my propane. I use something like GC mass spectrometry to figure out what the percentage of the two products are. And so I have the percentage of product A. And what that's going to be based on, well, my percentage of product A is basically, I need to normalize that. So I'm going to divide percentage of product A by the number of A hydrogens, by the number of proton, or by the number of A's hydrogens that give me product A. And if I do that, I'm going to make what's called a selectivity of forming the primary radical, basically. So that's going to be the selectivity of, it's going to be the rate at which I form the primary radical. And if I do the same thing for B, I say, well, I'm going to take the percentage of product B and divide it by the number of B hydrogens, then that's going to give me the rate at forming the secondary radical. Now, these are absolute numbers and they can't be determined, is the problem. But I can determine the ratio. I can determine the ratio of forming the secondary radical versus forming the primary radical. And so I just simply divide these two together. So I would say that the rate of forming the secondary radical over the rate of forming the primary radical is equal to the percentage of product B divided by the number of B hydrogens over the percentage of product A divided by the number of A hydrogens. And so that's the only way I can get at the relative rates of forming a secondary versus a primary. And I could do the same thing for a tertiary versus a primary. Or I suppose I could do it tertiary versus secondary versus primary. But I kind of do them individually. So people have done this with a wide variety of compounds. And so what they've done is they've kind of averaged out this rate of forming the different radicals, which I'm going to call the selectivity. Okay. And when you do that, what you're going to get is you're going to get the following ratios. And I'll always give you these. They may vary a little bit from book to book. But for bromination, we form a tertiary radical. The rate of forming tertiary radicals to secondary to primary radicals is 1700 to 80 to 1. And this is bromination at room temperature. For chlorination at room temperature, tertiary, the rate of forming a tertiary radical to secondary radical to primary radical is 5 to like 3.4 to 1. So what does that mean? That means for bromination, we form a tertiary radical 1,700 times faster than a primary. And you form a secondary radical 80 times faster. For chlorination, it's only 5 to 3.4 to 1, so those ratios are much smaller. And so now, and that's what's measured experimentally, and that's what we're going to use. Because I can rearrange the formula that I wrote on the previous slide, and I can basically say, oh, the percentage of product A is equal to the number of A hydrogens times my selectivity that I now know. And the percentage of product B is equal to the number of B hydrogens times the selectivity. this is a lot of math for organic. But don't worry, it's not that difficult. That's going to be like 3 times 3.4 or 2 times, well, actually, it's never 2. It's only 1 times 1700. So that's how we can calculate what our percentages should be. I just need to know what are my conditions, what am I using, bromine, chlorine. So I just need to know selectivities. So if I go back then to the original problem, and I'm just going to put the bromine over here, so that's still 1 bromopropane versus 2 bromopropane. What's the major product of this reaction? I'm doing this, let's say at light, at room temperature. I can now go ahead and calculate. So the percentage of product A, well, percentage of product A, there were 6 hydrogens times what type of radical formed product A? Primary, secondary, tertiary. Primary. So that selectivity is 1. So it gives me a number of 6. For 2 bromopropane, how many hydrogens? 2. Times what's the selectivity for bromination at room temperature? 80, 160. So we take the number of hydrogens times the selectivity. That gives us a number. The product with the biggest number is the major product. It's as simple as that. And so that takes into account the statistics and the favorability of forming the different radical intermediate. Now, if somebody said, well, what's the percentage? The percentage of B is equal to 160 over 166. It's just like GC, I add up the numbers. So by my counting, that's over 90%. And the percentage of A is 6 over 166. Just for fun, let's switch to chlorine. What's the major product going to be when we switch to chlorine? So we do the same thing. Pentane plus chlorine with light at room temperature. I'm going to have my 1-chloropropane, product A, my 2-chloropropane, product B. Same formula, except now the selectivities change. 6 hydrogens times the selectivity is 1. That never changes. Whenever you're making a primary radical, the selectivity is always 1, because that's what the ratio is built on. What is it for 2? 2 hydrogens times 3.4. So I still favor product B by a ratio of 6.8 to 1. So if I was to calculate the percentage of B, it would be 6.8 over 7.8. Again, the bottom number is always the sum. Would it be 6 times 1 is equal to 6. So it'd be, Yep. Okay, it's 8 o'clock in the morning. Simple math at 8 o'clock in the morning is still hard. Inorganic. This is why we don't do a lot of math in organic. So let's just take a step back. When I did bromination, I got 90% 2-bromopropane. When I do chlorination, I'm getting what? A little bit over 50%, but really it's a 50-50 ratio, almost. And what's driving that 50-50 ratio is that the selectivities are closer together. They're just talking pure numbers here. The selectivities are closer together so that the statistics plays a bigger role. With bromination, I would need 80 primary hydrogens to tie with one secondary hydrogen, basically. Over here, I would only need 3 secondary hydrogens to tie with one, or 3 primary hydrogens to tie with one secondary. So the numbers are closer together, which means chlorination is going to give you a wider distribution of products versus bromination. Bromination is going to tend to give you a single or a couple single major products because of the numbers. And I'm going to say that bromination is more selective than chlorination. So much so that the major product, if I've got just secondary hydrogens for bromination, that secondary hydrogen is going to be the major product. If I got a tertiary at 1700 to 1, nothing beats a tertiary. So the bromination is going to occur almost exclusively at the tertiary position. So this formula then of multiplying the number of hydrogens by the selectivity is how we can estimate what the major product is. And like I said, I will always give you these selectivities on the exam and the final exam. Is everybody kind of with me here? I've got plenty of practice problems because as you can see, I could ask you the same problem and you do it for bromine, then you do it for chlorine, and then we'll deal with what happens at greater than 300 degrees, and I'll even throw in fluorine for fun. So that's how we do the calculation. Okay, so everybody okay so far? Why are they different? Why are the numbers different? That's a rhetorical question that I will answer over the course of like 10 minutes. Why are they different? And here's the real question. So when I take if I take my propane and I convert it to the primary radical in the rate determining step of the reaction. So the rate determining step means that my halogen atom abstracts the hydrogen to form that radical. So this is propagation step 1. Propagation step 1 is the rate determining step. So one of the things that we have to think about here is, okay, I'm forming the same primary radical in bromination and in chlorination. Or I'm forming the same secondary radical. So why are the selectivities so much different? It's not dependent on the structure of the radical, because they're the same. So it must be something about the halogen itself. So think about this. I'm forming the same primary radical. I'm forming the same secondary radical in my energy coordinate diagram. But what's going to be different? What's going to be different is the starting energy of the reactants. The propane's the same, but the halogen radical is going to have a slightly different energy. So here's what we need to know. We need to know that for bromination, the reaction is endothermic. That step is endothermic. And for chlorination, that reaction is exothermic. Now, again, if you're saying I didn't draw these exactly right because basically this energy and this energy should be the same for the radicals. So if you could imagine that that's the end point, one's going to be exothermic and one's going to be endothermic. So now we have to invoke Hammonds Postulate. And so we invoke Hammonds Postulate by basically thinking about, it's King Lear. I cannot read Shakespeare in a King Lear-like voice, so we'll just use the piece of paper. Let's see, your direction, endothermic. Right, endothermic. Exothermic. Which one has the bigger transition state energy? No, sorry. Modify my question. Which one has the bigger activation energy? Exo or endo? Just say it. Say it one more time. Thank you. Endothermic has a larger activation energy than exo. Which one should go faster? Exo. The exo reaction should occur faster. So remember, what Hammonds Postulate tells us is that basically for an endothermic reaction, the transition state looks more like the products, which then results in a higher activation energy. Hammonds Postulate says for an exothermic reaction, the transition state looks more like the reactants, and so it has a lower activation energy. Hammonds Postulate really doesn't say any of that. That's what we interpret it to be. So if you have an exothermic reaction, if your transition state looks like your original reactant, you only have a few bond moves to get to the transition state. Fewer bond moves means less energy is required. The more energy you got to put into it, the longer it's going to take. Now, the activation energy related to rate is not Hammonds Postulate. It is the Arrhenius Equation. So in the Arrhenius Equation, what we know that the rate is equal to some prefix times e to the minus a over RT. And so mathematically, the lower the EA, the higher the rate. And Arrhenius Equation also tells us about the rate of the temperature, the role of the temperature. Okay. So this is why bromination is more selective than chlorination, is because they have, one is exothermic and one is endothermic. Okay. So let's just take room temperature. Molecules have a certain amount of kinetic energy. That kinetic energy is proportional to temperature. Right? That's from general chemistry. So those molecules then, if they're facing a higher activation energy, they are going to form the product. In this case, they're going to form the intermediate slower. If it's an exothermic reaction, they're going to form the intermediate faster. Is everybody with me so far? I didn't explain it. I didn't really actually get at the why is forming a secondary radical faster for chlorination, or why are the relative rates closer in chlorination and more broader or more farther apart in bromination? Okay, I haven't gotten to that question yet. In order for me to get to that question, I now have to look at these diagrams in more detail. So let's take chlorination first. So chlorination goes here to form a primary radical, and it would have something like that diagram to form a secondary radical. Because remember, secondary radical is more stable than primary, so it'd be a lower energy. So which radical is going to be formed faster? Secondary because of Hammonds postulate. Now what I've done is I've made the intermediate more stable, and that has pulled down the activation energy. Okay, so we will form the secondary radical faster than we will form the primary radical. But isn't that going to be that's going to be the case both for chlorination and also for bromination, because I basically have the same diagram, right? Primary radical versus secondary radical. So I'm always going to form the secondary radical more quickly or faster. But remember, this is basically like 3.4 times faster, and this one is 80 times faster. So it's the idea of the exothermic versus the endothermic that is going to give us the difference in the relative rates. So when we have a chlorination, since this is exothermic, the relative differences of the activation energy is going to be smaller for chlorination. So that means I'm going to be forming the secondary at not exactly the same rate, but only a little bit faster than the primary because the activation energies are so small. So here's my bird hiker analogy to this. We have birds and or hikers that have considerable amount of energy because they're at room temperature. And there's two hills in front of them. Two small hills in front of them. So as they're going over those hills, they will always go over the smaller hill faster. But since they're small hills, the rates of them going over those two hills is going to be not exactly the same, but there's only going to be a small difference. Okay. Now, if I starve the hikers/birds for energy, those differences in the hills might become more accentuated. Right? Because now they're not just jogging over the hills, they're like on their hands and knees trying to crawl over the hill. But still, because they're small hills, there's going to be a smaller difference in the rates of going over those. And this is the non-mathematical treatment of that. If you wanted to, you could go through the math and the Arrhenius Equation and show how the rates are actually not that much different. But that's what our experiment did. That's where the 3.4 to 1 comes from. That's what that's showing us. So then we go to the big mountains, which is the bromination, because it's exothermic. So now hikers/birds with lots of energy, they're faced with two much larger mountains, different sizes. They're still going to go over the smaller mountain faster, but now the rates are going to be different because those mountains are so much bigger. And if you starve them for energy, it's going to become even a bigger difference in rate. Right? The birds don't have enough energy to get over one mountain, so they smash into the side of it, but they can just barely make it over the small one. As an extreme example.
So if you were to hit it, you can't select the primary radical always, because there will always be a secondary one that forms it.
Yes. So if everybody's okay, we can move on to the heating situation. Does that make sense with the size of basically the activation energy, that when you've got small activation energies, because the reaction is exothermic, the differences in the rates are going to be much smaller? Whereas if you've got an exothermic reaction, the differences in the rates are going to be much bigger because it's just bigger mountains to go over, bigger activation energies. Does that make sense qualitatively? I see like 5 heads nodding. Jake?
Could you select a secondary radical almost 100% by doing the reaction with light but at a cooler temperature?
Eventually you could get it to a point where you would have a maximum selectivity. But here's the problem with starving the system for energy. It still has to react. So you might get to a point where you would get 100% secondary and no percent primary, but you're going to be on the edge of getting no reaction. So you have to kind of be careful about that. And with the Arrhenius equation, of course, the Arrhenius equation would be your exact solution. So you're now bordering on chemical engineering. Sitting down and figuring out all the gory math to try and figure out, okay, exactly what temperature would I get my maximum secondary to primary ratio? But you probably still would get some primary. So now let's talk about heating. As I heat the reaction, what's going to happen to the relative rates? The relative rates are going to get smaller, right? It's not going to be 80 to 1. It's going to be 70 to 1, 60 to 1, 50 to 1. Because as I give the molecules more energy, they're able to overcome both barriers faster. And at some point, it's still going to overcome the primary slower, but those rates are going to be almost indistinguishable. So our selectivities then, if we choose a temperature, and typically greater than 300 degrees Celsius, the temperature that's selected, because mathematically that all works out. Basically then, our tertiary to secondary to primary would be like 1 to 1 to 1. So the rates are going to be nearly identical. I mean, mathematically they cannot be identical, but they're going to be close. So that means that at that temperature, I'm forming primary, secondary, tertiary radicals all at the same rate. Okay. If we want to go to birds, we now have supersonic birds. They could probably go through the mountain if they wanted to, but they can go over any mountain equally fast. So now all of a sudden, these would be the selectivities for either bromination or chlorination. So once we go to 300 degrees Celsius, there's no selectivity, which means in our formula of percent product equals number of hydrogens times the selectivity, if the selectivities now all become 1, what happens? It's now totally based on statistics. So it's totally based on the number of hydrogens. So going back to the propane. Going back to the propane, we'll go all the way back here to the propane. So going back to propane, we had 3 times as many A hydrogens as we had B hydrogens. Basically, that means that at best, I could form 75% A and 25% B. Because it's a 3-to-1 ratio, so A would be 3 out of 4 and B would be 1 out of 4. So the best I could do for that reaction is a 75-25 ratio. Which means there's no way for me to form 100% of A. I'm still going to get 25% B. And that doesn't necessarily matter in this class because we're just writing the major product or writing all the products and then circling the major one. It's normally how I ask these questions. But in a real world situation where you're in a plant and somebody comes in and they say, hey, I want you to make 1 bromopropane. And you go, okay, well, I can do that with free radical halogenation. I'm going to set my reactor temperature to 300 degrees Celsius so I get 75% of A. I'm still going to get 25% of B. I still got to separate the two. And then I got to figure out what to do with B. Hopefully another person comes along and says, hey, I want 2 bromopropane. Because then you can go, oh, well, then I can sell you that. Right. So halogenation reactions are never 100% of one over another. Now, even if you had a tertiary bromide, it would still be 1700 to 1. That's pretty close to 100%. But if you have a primary hydrogen, you always have to have 3 primary hydrogens. You can't have any less, right? Because that's, well, you could have less, but not in a normal alkane. Right. So this is how those selectivities change. They don't change because the radical is different. The radical is the same. What changes is the reaction coordinate diagrams. Those change from being endothermic to exothermic. And then what can also change is the temperature to force you to go over the barriers at nearly the same rate. And if you want to lower the temperature to get a maximum amount, at some temperature you're going to get no reaction, so you got to be careful. So that problem is why we don't have iodine. Because iodine is very, very endothermic to the point where the reaction doesn't go at room temperature. And the problem with fluorine is that fluorine is so exothermic that it just explodes. And then you can't collect the products when whatever you're doing it in is exploded all over the place. Jake?
So could you tell based on the ratios whether or not a reaction is endothermic or exothermic, and then how endothermic or exothermic?
Yeah, you could probably go back and work back through all of the math and calculate the activation energy. But the problem is if you want the activation energy, that just tells you the difference, and so you've got to anchor one of these before you can. Like if I know the activation energy is 5, but I don't know either one of these two energies, I just know it's 5. If I have an idea of what this energy is, then I can back calculate. But remember, this is the activation energy, right? So yeah, I could go from here to here as 5, and where do I put this in? So, I mean, this is the gory details that you would probably only get into if you were in really looking at the mechanism of this or trying to engineer the system. But it is doable with the Arrhenius equation. We're not going to do that. We're just going to take a reaction and say, what's the major product, and we're going to use the selectivities. So then you'll see greater than 300 degrees Celsius, bromine or chlorine, and then that's also the selectivities for fluorine at room temperature. Just simply because fluorine is the most reactive. And because fluorine is the most reactive, that's why we have like Teflon. Right. The reason we have Teflon is because of the reactivity of fluorine, and also because of the atomic bomb project. Because what they were doing in the Manhattan Project was they were converting uranium into uranium hexafluoride gas so that they could separate the two isotopes of uranium by diffusion or effusion, by putting them through different barriers of different pore sizes. And what happened was that the fluorine gas would destroy the stainless steel or anything else it came in contact with. So that's why they needed to make Teflon to coat the inside of the stainless steel, because fluorine would not react with Teflon. And Teflon is just simply a long chain carbon with nothing but fluorines on it. It's fallen out of vogue in cookware. Right, I used to have Teflon cookware, but now that's apparently bad or evil, depending on your point of view. So it's still out there, and it's still out there as a plastic material. So that's how we got developed, because they needed something to coat the steel with, because otherwise the fluorine would destroy it. So out of the Manhattan Project, we have Teflon and atomic weapons. So that's why we don't react fluorine with hydrocarbons, because it's just too reactive. But if we did, it would be 1 to 1 to 1 at room temperature. Okay. So that's where the selectivities come from. That's why they're different. And so now what we need to do is do some problems to try and figure out, okay, if I gave you pentane and said, I want you to react pentane with chlorine at room temperature, and then with bromine at room temperature, and then with either at greater than 300 degrees Celsius, would you be able to calculate and tell me what the major product and what the percentages of those products would be under each one of those circumstances? Okay. Which sounds like a good take-home quiz problem. But what I want to do in the last couple minutes is I want to kind of set what we're going to talk about on Monday with these free radical halogenations. So right now, the most stable radical that we could form is a tertiary radical. Well, that's true, but there are some more stable radicals that we could form that would form as part of a free radical halogenation. I'm not going to put numbers to them. So for instance, that hydrogen is called an allylic hydrogen. The allylic position is next to the double bond. That allylic hydrogen will form an allylic radical. What's going to make that allylic radical stable? One word. Resonance. So, and then you say, well, wait, I sort of remember how to write resonance structures with carbocations moving arrows. How would I do it in this case? I would take this, I would break the double bond up, and I would pair one of its unpaired electrons with the unpaired electron of the allylic system, and then I would give the other unpaired electron to the end carbon so that I would form that resonance structure. So in essence, the double bond moves, but not because it's a pair of electrons moving. It's because I'm basically pairing up that unpaired electron with one of the two electrons in the double bond. So the allylic position, the allylic radical, is very stable. Even though in this case it's a primary allylic radical, because it's got resonance structures, it's more stable. If it was a secondary allylic, it'd be even better. And if it was a tertiary allylic, it'd be even better than that. So what does that mean? That means that if I took this molecule and I said, I want to react this with bromine and light, what product would I get? And bromination, as we saw with all the numbers, the bromination, the major product's going to be, you're going to replace a tertiary hydrogen if it's there, and then if it's not there, a secondary hydrogen, and there's always going to be a secondary hydrogen. So it's going to replace the most stable, the hydrogen that gives you the most stable radical. How about that? So what's that going to be in this case? The secondary, but also the allylic. That's the whole discussion was over allylic. So, what's your product of your reaction going to be? You're going to do free radical halogenation at the allylic position. Always. That's going to be the major product. So whenever you do free radical halogenation, you're always going to halogenate at the allylic position. Or what kind of carbon is that? What would it be called? That's the benzylic position. Right? If I took my hand and I covered up the ring, or covered up part of the ring, which doesn't work when I cover up the computer, it doesn't show up on the screen. But if I covered up part of the ring, what would I have? An allylic carbon. Except when it's attached to the benzene ring, it's called benzylic. It's going to be the preferred position of forming a radical when you have a benzene ring. Why? Because when I form that radical, how many resonance structures can I draw there? More than one. So allylic and the benzylic positions are going to be my preferred free radical halogenation positions. They're going to be what's preferred. And I'll have to come back on Monday real quick and actually modify this reaction right here. I'm going to have to modify that reaction because actually the allylic bromination is not what happens in that reaction. So do we have, let's see, we have a take-home quiz, and I'll write this out on a piece of paper. I would like you to write all the possible products of chlorination, bromination, of pentane, and then for each one calculate the percentages that you would get under those three sets of conditions. Your take-home quiz for next Wednesday is at least going to be to write a free radical mechanism, all 6 steps. But we'll get to that on Monday. All right, so I'll send that out when I get the website updated. If you have any questions, email me or stop by. Otherwise, I'll see you on Monday.